My name is Sinan Kochara. I'm from Arkansas. I work with my colleagues and Malai. These are my undergraduates contributing in the research. Thank you. So, introduce a soft Kinetic structure for Dermoscopy images. First, I'll introduce the background. What is dermoscopy? Why border detection is important. Then I'll give you technical background a little bit. Then overview of our framework. Then how our hierarchy is created and its properties. Then experiment conducted with the Dermoscopy images, and we also do well-known two graph-based image segmentation algorithms, and then the results. Then I'll introduce the conclusion section. So, melanoma is the fifth most common malignancy, and it's very dangerous in the world. Most deadly in this paper from this people died. So since melanoma is the one of the type, simple excision operation. What is dermoscopy? Especially skin border is important, especially cases border. Latest first recently developed in storing and update, but motion. What does this mean? Balls or in the nature, so what they for trajectory. Just we for maintaining the, and it is go. So based on this, so minimum strength 3. If we have our graph, scenario there is no side. U and V. So if we are considering multiple T spanner distance between two vertices in the should be smaller or equal to T times this distance in the origin is 1. So this distance in the this should be multiplicative 3, 4. If we compare, then it will be 3 because in two vertices in the spanner and in the original graph. So S and T are constants. These are given. Use first rule that is they are only affected small subset. Second, they are uniform. One combinatorial edge. Third, what does this? We can produce descriptive more tightly or more loosely, and discrete geometric coordinates we have on the edge. Proximity based. So all images are represented generally as graphs. If we have and these are pixels E and Q, and similarity between these two is represented as C code function. It can be color difference and also spatial difference. So we represent the graph as fully connected graph. Note for each and every pixel the corresponding node. So there is each and every pixel there is an link with the cost as similarity between the pixels. So what we do if we overview, we have sample data set 100 dermoscopy images, ground images as well. These are drawn by a dermatologist. We get our image, create our hierarchy, so kinetic Euclidean minimum tree. Then by doing segmentation, traversing the tree. So after the segmentation, we find the precision recall and border error, which will be extracted on. Then we do comparison between segment image and ground border images, and we found precision recall errors. So overall scheme is listed here. What we have original image, we create our hierarchy. We called it Ball's hierarchy. And as you can see, each branch of the hierarchy is corresponding to one segment. So it was interesting to find out that after the root, each branch is corresponding to one of the segments. And border is represented in here. So the smallest branch is generally border. So, indeed, this is important edges. One average, other one child. What is average? There is two cluster balls, and distance between more than or equal to negative times expansion ratio. The radius. I'll explain it. Neighbor constant in this between any constant. It will be clarified. We also checked all this thing. If there is a and it is covered by another parent-child edge. So, to create a hierarchy and properties. So, I'll first points. Each point is a center. Each point center will be covering automatically decreasing or refine the representative cluster balls. The initial level first point is child edge. So we talk distance between any the hierarchy construction. Both center is covered. There is not covered by the upper. A cluster ball parents itself. At the same level, two must be cousin relation. Always U at level R always parent chain for the same data set. Hierarchical structure. The different cool We'll assume that in the second layer, before becoming must be neighbor edge. If they first child-parent relation, neighbor coefficient must expansion ratio. So if cluster ball in expanded to second vertices, red these red ones want third ball V possible. Blue lines are back one is and last one the hierarchy. Yes. For the sake of hierarchy run selecting a point. So first P0, we got P0. So we are looking for the very first ball cluster. There is nothing else in the radius with. So it goes to upper level. Expanded. So expansion ratio in this example is 2. Minimum radius is 0.3 and net coefficient is 3. So goes to next level. At that level comes 0.9. So same point in two different levels. Now second point comes. First point was that one. Second point comes. In this level always will be presented. Expanded to the second level. Now there is neighbor relation between these two. So we create net between these two. So at a single time we always say root. So in this case, any one of them will be root. If equality holds, exact equality between these points, we randomly select one of them as a root. So the second one is selected root. So it's expanded to one upper level, blue. Now new point comes. How is represented in the hierarchy? We have 3 as a root and 1, 2 as our hierarchy representation. Now new point comes 4, 5, 0. The first level it will be always be represented. Goes second level, we expand. Right. So there is neighbor relation in these three. So we create our neighbor edges. So since in the upper level new point is already covered by the blue, which is 3, so it becomes child of it. Next one comes. So in the first level, always will be represented, and to the second, still it's not covered. So will be expanded one upper, all right? Expanded to the one upper level. So is there any neighbor? Yes. So we create neighbor edge. Since this first one has more children, we select that one as our rule. And so hierarchy is created. Now we didn't mention this in the paper because of the limited space. How it behaves to the movement. For the movement, we have promotion, demotion. For the promotion, we already have this point, and it is node 5. Here it is. Then it moved from this location to here, out of this covered level. Goes to here. Then, since in this level it's covered, it needs to be promoted to the upper level. Goes to the upper. Then it becomes neighbor with these in that level, blue ones. What happens for the demotion? We already had a point here. As you can remember. Then it moves to here, goes to this 8 to the root. So what does it previously? It was represented in that level. Now it is already, if it moves to here, then it's by this root, right? So it is demoted all the way down to the lowest level, because in the second level it's already covered by this. So demoted, since it doesn't have any child itself, it's also goes one level low. So in these examples, most important is the expansion ratio. If it becomes closer, then original graph is represented very fine. If we make it larger, it's represented as more coarsely. Okay. If it becomes expansion becomes smaller, then as you can see, number of levels increases, and the number of edges increases again. For the precision, always having smaller expansion ratio is good, but the computation time will be slower. So if we summarize it again, we have our original image. We have also hierarchy indexers, which creates IDs for pixels. Then once we create our hierarchy, each branch will be representing different segments of image. So then we, after creating these segments, we compare automatically obtained from the algorithm that is blue in the sample. Image is manually born from a Dermoscopy list. So the red one, so we find the precision and also in 2000 is another measure for the border, and we use that. So for Dermoscopy images, as I said, most important thing is the ratio. So we try to find the most efficient expansion for sample images. we found 1.2 is the most efficient. Here are some results: original image, physician manual image, and overlay image is red, drawn by Bolsky. And as you can see, it's pretty close. So we also compared our Bolsky with normalized and the efficient graph based. For a simple sample, we obtained these segmentations. For the efficient graph based segmentation, we obtained these. Normalized time and overall precision and recall for 100 images is precision, 67% recall rate. So fine border it's not very efficient. Also EGS efficient graph segmentation, it also have recall 55%. And computationally this is very expensive, ON cube. And the second one, unify the difference parameter, and it is MP. So in order to find maximum performance for this algorithm, the tedious experiment practice process. For ball hierarchy, it's n log n, but sure we are trying ON computation time. Precision is 100% because a little bit over than 90%. Border is 2.28. So as you can see, for this sandwich is the most effective one. So as a conclusion, with computation algorithms, it's first of all of images like video. Second, except operations is again operators Mutlu and Kemal Aydin and Vincent now in person, his PhD in Oregon State, Brandon Lee, my undergraduate student in University of Arkansas. All right, thank you. Thank you.